Okay, we'll start with problem number 1 in the worksheet from last Friday, refraction and light problems. So number 1 says a certain radio wave has a frequency of 1.7 times 10 to the 6 hertz. What is its wavelength? So which equation are we going to use? First one, so we're going to do C equals F lambda. What's C?
Speed of light.
Speed of light.
10 to the 8th. Let's go.
So 78 meters per second. You're on your game today, Michael.
It's a shocker.
Alright. What is 1.7 times 10 to the 6 hertz? Frequency. We're going to use F. So. Okay. So we just divide that out. And what do we get for our wavelength?
176.47.
Alright, any questions on that one? You took the what? Carries it.
Okay, good then. Oh my gosh, thank you for waiting.
Alright. Number 2. A ray of light passes from air into carbon disulfide at an angle of 47.6 degrees to normal. What is the refracted angle? Alright, so one thing you do need to know is that air, the index of refraction is 1. So it's going to be n equals 1. So the equation we're going to use for refraction is n1 sine theta 1 equals n2 sine theta 2. So 1 is always what it starts in, 2 is always what it ends up in. So what's n1 going to be? 1. The next refraction of air is very close to 1, so just say 1. What angle does it start out going at?
47.6.
Yep. 47.6 degrees. What's the index of refraction for the material it enters?
1.60.
And we're looking for the angle it leaves at, it's theta 2. So we're going to take 1 goes away. Sine of 47.6 divided by 1.63. And what's that equal?
29.2.
Okay. Make sure your calculator's in degree mode, guys. What do we do to get theta now?
The inverse sine of 0.45.
Inverse sine of 0.45, so we get theta 2 equals.
Someone's at the door.
How do you do that? The inverse sine?
Inverse sine.
I
So you-
tried that. I know how to do inverse.
Second sign on your graphing calculators usually.
Yeah.
So you second sign 0.45.
She's in
Right.
radians, it's fine.
Yeah, we're
Make sure you're in degree mode.
I'll blame it on you though, he's kind of
Sorry.
Alright, can I erase this?
Absolutely.
Absolutely. Alright. Number 3. A ray of light passes from air into ice at an angle of 38.9 degrees to normal. The refracted ray of light then passes from ice into glycerin what is the angular refraction of the ray of light in the glycerin? So what's going on here? We have air, ice, and then glycerin. So it goes into the ice, refracts, and it keeps going at that same angle till it gets to the glycerin and refracts again. So that's the angle we're looking for. Does that make sense to everybody? Okay. This angle right here, that's the angle it gives us. That's what's going into the ice at. And what's that angle?
38.9.
38.9. Now, we can find this angle using Snell's law. And what's going to be true about these two angles, since everything's parallel here?
Congruent.
They're equal. So that's equal to that. So if we find this, we're going to find this one, and then use that as the entrance angle for the ice and the glycerin. So again, it's just a two-step problem. Does everybody see how that works? So first we do 1 side, theta 1, and 2 side, theta 2. What's N1 for this first part? 1. And I'm going to do sine of 38.9 degrees. What's N2?
1.309.
1.309. And then we do sine theta 2.
$28.67.
28.7 degrees. Questions how I get that first part? Alright. Now same thing again. Same equation. What is our index of refraction for what it starts in for the second part? Okay?
Sorry, this is a question. Is theta 2, which angle is that?
Theta 2, theta 1 is one is what it's going in as.
Okay.
So N for like this part is. Theta 2 is what it's going out as. So it goes in at 38.9, bends, and then leaves at 28.7.
So that other mark is at 38.9.
No.
I thought we said that.
So what we found here is this is 28.7, and this is 28.7.
Oh, okay.
So both of those angles are 28.7.
Oh, okay.
Makes sense?
Yeah.
So what's the index of refraction for the second part for the what is starts out at?
1.309.
Yep. And we just said it enters an angle of 28.7 to do sine 28.7 degrees equals what's the index of refraction for what it's going into?
1.471.
We do sine of theta 2. So this is what we're finding right now, so that's our final answer. $25.3. Questions about that one? You guys understand what went on there? Alright, we're gonna do one more together, and then we're gonna go over the equations and probably one or two problems from the next sheet as well. Alright. Can I erase this? Alright. Number 4, the critical angle for refraction of a certain material is 58.8 degrees when it forms a boundary with water. Use this information to determine the speed of light in the material. Okay, when it says the critical angle for a certain material, that means it has to be going something from start out in a high end value, which is that material. So what we're going to be looking for is the N1 is going to be the material, N2 is going to be water. Does that make sense? Since it's for it to have a critical angle, it has to be going from that material. You guys can understand that? So, first equation we're going to use is sine theta c equals N2 over N1, and we're going to be solving for N1. Does that make sense to everybody? Once we have that, we're going to use N equals C over V to find the speed of light in that material. And what's the speed of light in that material going to be in that equation?
C.
V. C is the speed of light in a vacuum, and that slows down or gets into any material. So V is the speed in any given material. So we're going to do sine. What's the critical angle? 58.8 degrees equals N2 is the water which it would be going into, so that's 1.33 over N1. And what does N1 equal?
1.55.
And then we go 1.55 equals 3 times 10 to the 8th over V. And what does V end up equaling?
Whoa. A big number for the. Yeah.
1.9
That
times
number.
10 to the 8th, yeah.
0.9 times 10 to the 8th meters per second. Any questions on that one? Alright, you guys are going to have some time at the end of class to do the rest of those. We're going to go through the variables and probably just do a problem or two on the one I just gave you. Okay, so these are equations for finding where images form and what the magnification is in mirrors. So you see the equations there. So right now what the variables mean, F is the focal length. The O is the object distance, so that's like the actual real thing that's being reflected. The I, image distance. Magnification is unitless. That's how many times bigger or smaller something is. HO is the object height. HI is the image height. And last thing is R is the radius of curvature. One important thing to note is that it doesn't matter what the units are, so you don't need to like convert centimeters to meters as long as they're all the same. That's only for these equations. When we're just using in the last section, you do need to have everything in meters, but for these equations, the units don't matter. They're usually going to be given in centimeters, so if everything's in the same unit, you don't need to convert. Does that make sense? Okay. So if you look at kind of that next section, the formatting got a little messed up there. So for a concave mirror, the focal length is positive, and for a convex mirror, the focal length is negative. So you have to make it positive or negative. For a real image, the image distance is positive, and for a virtual image, the image distance is negative. If it's larger, m is going to be greater than 1. If it's smaller, m is going to be less than 1. If it's inverted, m is negative. If it's upright, m is positive, and the object distance is always positive. So kind of, for the positives and negative, anything in front of the mirror is positive, anything behind the mirror is negative. Does that make sense? Alright. Let's look at number 1. A concave mirror forms a real image at 16.6 centimeters from the mirror surface along the principal axis. What is if the corresponding object is at a distance of 34.5 centimeters, what is the mirror's focal length? Right. Erase this. So what equation are we going to use for this one?
1 over
Yep. 1 over f equals 1 over EI plus 1 over EO. Alright. So we have 1 over f. So we're looking for f. What is our image distance? 16.6. Should that be positive or negative? Positive. Because it's a real image. And real images form positive, or are positive in these equations. You can say everything's in centimeters, so I'm just going to keep it in centimeters. What's our object distance?
33.5 centimeters.
And object distances are always positive. So what's 1 over 16.6 plus 1 over 34.5? Zero what?
8, 9.
So what's the focal length equal?
11.2.
That makes sense. And we have a concave mirror, so it should be positive, so that makes sense. Questions on that one? Right. Number 2. A convex mirror of radius 24 centimeters has an object placed 5 centimeters from its surface. What is the image distance and magnification of the, should say, of the image? Also state whether the image is real or virtual, inverted or upright, larger or smaller. So we're gonna start off with this, but do we have focal length? So how do we find focal length here?
R over 2.
Yep. So we do f equals r over 2. F equals, what's r here?
24.
24 centimeters for 2, so f equals 12 centimeters. So we start off with 1 over 12 centimeters. And should that be positive or negative? Positive. Why positive? Because it's concave mirror. Does that make sense to everybody?
Yeah.
We don't know our image distance. What is our object distance?
5.
Yep. So we end up with 1/12 minus 1/5. What's that equal to?
1/12 minus 1.
Yep.
19 over 300.
Give me a decimal.
0.063. Is that, I just said 1/12 minus 150.
Huh? So,
Sorry.
okay.
Didn't get that.
What did you guys get? Should be negative first.
That's just
Oh, that's
One-
1/5. I
one
had 1 over
sixth.
50.
Yeah.
The C looked like
Okay.
a zero.
Did you say 1/50?
The C
Yeah, the
does
C
look
looked like a 0.
Okay.
Sorry.
That's okay.
Negative 8.57
Negative 8.57
centimeters.
centimeters. Okay. So that's our image distance is negative 8.57. What kind of image does that mean it is? Virtual, so that means it's behind the mirror. And now we're going to find the magnification. We do negative di over do. We get negative 8.57 divided by 5.
Negative 1.7.
Were the negatives cancel out?
Yeah, the negatives are.
Yeah.
So, thank you.
1.714.
1.714.
Yeah. Like I said.
Okay, so we have our, that's one answer, that's the other answer. So real or virtual? Larger or smaller? Larger because m is greater than 1. Inverted or upright? Upright because m is positive. If m is negative, then it's inverted. Any questions on this one?
How do we know it was virtual again? Oh, because it was negative.
Image distance is a negative.
Isn't it smaller though? How did it get larger? What were we comparing?
M is greater than 1.
Oh, it's smaller.
Any other questions on this one? Alright. I'd like to do one more together, then you guys can have the rest of the time to work on the rest of the problems on your own. Can I erase this one? Alright. A convex mirror has a radius of 26 centimeters and has an object placed 31 centimeters from its surface. The object is a pencil that is 15 centimeters tall. What is the height of the image? Alright, so we're going to have to find the focal length again first. So F equals R over 2. And what's the radius?
26.
26 centimeters over 2. So F equals 13 centimeters. Should that be positive or negative? Negative, why? Because it's a convex mirror. Okay. So we're gonna have to use the 1 over f equation because we're looking for hi. We don't have magnification and we don't have di, so we can't do anything to find hi yet. And do 1 over f equals 1 over di plus 1 over yo. 1 over negative 13 equals 1 over di plus, what is our object distance? What was it?
31.
31 centimeters. So what's 1 over negative 13 minus 1 over 31?
I'm gonna make sure I do it right this time. That's what I want.
And what is our image distance equal here?
Negative 9.6.
Okay. So does that mean this is real or virtual?
Virtual.
Virtual. Is it possible at all, since DO has to be positive and F is always negative for a convex mirror, is it possible to get a positive image distance? That's why, you remember when we were doing the ray diagrams, we said all convex mirrors only make virtual images. So mathematically, do you see why they all have to make virtual images? Alright, and so now we have di. So with the equation we can use now, we can use part of that magnification equation. We can use negative di do equals hi or ho. So we got di is negative 9.16 centimeters over do, which is 31 centimeters. Hi, what's our object height?
15.
15 centimeters. Good. Negatives cancel out, there we get 9.16 times 15 divided by 31. And what do you get?
4.03.
And you notice it is, just like we said with all convex mirrors, it's upright and it's smaller. So the image is upright and it's smaller because hi is positive and smaller than 15. Any questions about these? The image is 4.43 centimeters tall, the object was 15. Yep. And if you found the magnification, it would be smaller, like m would be less than 1. Any questions about this one? Alright, well you guys try to finish the last 4 on that mirror sheet and the last 4 on the refraction and light problem sheet. I have the answers to